part 2 of today's session, complex power flow. From the conservation of energy, it should be clear that the real power supplied by the source is equal to the sum of the real powers absorbed by the load. Yep. So what that's saying is all the powers used by the loads has got to equal or add up to the power being supplied from the source. Conservation of energy. You cannot create it, can't destroy it. You can only convert it from one form to another. Yep. This means that the total complex, so the balance between reactive powers must be maintained. This means that the total complex, or apparent power S, delivered to the loads in parallel is the sum of the complex apparent powers delivered to each load, such that for the following circuit, if the total S here is equal to the voltage multiplied by the total current flowing, them two, yeah, I times E, then we could say, because I, by Kirchhoff's voltage law, this total current here is equal to I1 plus I2 plus I3, Kirchhoff's current law that you should be familiar with. Then you can do that E times the bracketed current terms added together, and then you can separate that, so we can say that S is equal to the power absorbed by E1. So the S here is what's being delivered by the source, plus the power absorbed by the load Z2, plus the power absorbed by the load Z3. So that's Z1, Z2, shouldn't be Z, S, S1, S2, S3. Yep. This is supply and power, so we got power going from there and be absorbed by these loads. And these S's each consist of a P, a power part, and a Q part. A real power in watts and a reactive power in vars, yep, which we covered last week. So what we're going to do, because that will all become a bit clearer, is go through an example. But I thought before I do that, I'll just do a whistle-stop tour of complex arithmetic in both polar and rectangular form, so we just know what the maths is like. So I'm going to add a slide in here, or two maybe. Let's pull. I'll just add a new one in. Stick it in there. And title that complex number revision. Okay. We got two ways to represent complex quantities or vectors. I'm going to split the board in two, and over here, polar, and over here, rectangular, or sometimes called by our mathematicians Cartesian. Yep. And it's about being able to represent not just the magnitude of a quantity, but also its angle or phase. So in the polar, we have an axis like so, where at 0 degrees, 90 degrees is straight up, 270 degrees, 180 degrees is the left hand side, 270 degrees is vertically downwards, back to 0. We also sometimes call that, or more likely to work with that, as actually minus 90, as we discussed last week. Equally, we could work with these being pi over 2 radians, pi radians, 2 pi over 3 radians. This being back to pi, or 0 or pi, that is. Yep. So we go on the full circle, because sorry, yes, it's 2 pi, isn't it? Full circle is 2 pi. Yep. So that's polar. And then we represent a vector or a quantity by its magnitude and angle, the length of the line and the angle. So if that line is 5, whatever units it is, let's say amps, and that angle is 30 degrees, what we would do there is we would say that that vector is 5 amps angle 30 degrees. That one, if that's 5 amps and that angle in there is 60 degrees, we would write that blue one as 5 amps angle minus 60 degrees. It would be equally correct to say that one is 5 amps angle minus 300 degrees, positive 300 degrees, and you would get the same answer out of any arithmetic that you did with it. Okay with that? Yeah. And when we talk about these numbers, magnitude phase angle. Yeah, mathematicians have got some other names for them, but we won't worry about that. Rectangular, on the same axis, we have 0, j, minus 1, and minus j. Now, this is also j squared, right? That can be said to be j to the power 3. Yeah, because, new slide, j, the operator j, is equal to the square root of minus 1. Yep. Which if you try that on the calculator, you know you won't get an answer. So we can't have the square root of minus 1. So let's say, imagine we call it j. Yep. So j squared is equal to square root of minus 1 times the square root of minus 1. Yeah, so if we square a square root, sorry, hang on, that's that squared, and what happens to the square root symbol if you square it? It disappears, we end up with minus 1. And and that means we end up with, that's that, and we end up with minus j. Yeah. Because we end up with, if we square the square root of minus 1, we end up with minus 1. Yeah. And then when we do it again, we end up with minus j. Okay? Because minus 1 times j. So that's where we are on there. If we take, and I've been very particular about choosing 5 for that line there. If we take a vector here, yeah, the way this is expressed is in how many is it left to right or right to left, how many is it up and down. So if that's 3 and that's 4, and I had that as a blue, hang on, that's how that is, red, 3, 4. The way that vector would be expressed in rectangular form is 4 plus 3j amps, for instance, if that's current we're looking at. Yep. If we go with one over here, where that's 4 and that one's 3, the blue one would be minus 4 plus 3j. It's how many across. Negative is if you're going to the left of 0, and again the units on the end. So in these ones the units go after the magnitude and before the angle symbol. In this type the units go right on the end. And if we had one down in here, which is a column quadrant, let's say that's 4 and this is 3, that one would be expressed as 3 minus 4j amps. What you have to be careful of here is what will these ones in no way do they tell you how many amps are actually flowing, what the magnitude or length of these lines are. You have to convert them to polar form to know how many traditional amps are flowing. I mean, I know that a 3-4 triangle sides, the hypotenuse is going to be 5. Yeah? But in that form, they don't tell you anything about the actual magnitude of current flowing in amps. Because we've got another way of describing these is to talk about these being real, imaginary, that's the mathematical terms, electrically in phase component, out of phase component. If you're talking about forces, as this can come into mechanics as well, you'd talk about the horizontal and vertical components of a force that's acting at an angle. Yeah. So that's how they're represented. Now we need to briefly go through, and I'm not going to do any examples. Our examples are going to be the ones where we use it in the examples for this module. But how do we do some maths with these numbers? Yeah. So, maths polar. Right. Addition and subtraction can be done, but is clumsy and requires sine and cosine rules. For non-right angle triangles, you need to know a bit of geometry, and that's tricky. Yeah. So we don't generally do that. So easier to convert to rectangular and add and subtract. Okay, so we'll do that, and we'll do the easy conversion using your Casio calculators to be able to convert from one form to the other. Okay? Multiply. Example. 6 angle 30 degrees times 5 angle minus 20 degrees. Either of you remember how to do that? Yeah, you do. You multiply the magnitudes and you add I really ought to do this. I'm going to be pedantic about this. Add minus 20. Yep. So that is 30 angle 10 degrees. All right. So multiply the magnitudes, add the angles. What do you reckon we do there? Yep. So you divide the magnitudes. You do 30 divided by 5. An angle minus 20 minus 30. I deliberately picked that to make caution with your angles. So it's 30 divided by 5 is 6. Angle minus 20 minus 30 is, yeah, 10 degrees. Yep. The degree symbol is important. If you leave it off, the assumption is that's radians. Okay? So you could equally do the same method in radians. You need to be careful that your calculator is in the right mode if you want to do conversions. Yeah?
You were saying last week about making sure that the notation might be right for these parts.
Yeah.
If you so obviously it's 6 and then 10 degrees.
Yeah.
But you know, just above that we've got 23. Is that alright to leave that without the degree sign as long as
Yeah, because that's within the calculation.
So as long as the answer.
Yeah. I mean, well, I would suggest that you do that actually, just to be on the safe side. Yeah. 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 But what you don't have to do is you don't have to put if this is amps and volts, you don't have to put them in there, but you do have to put it in the final answer. That you have to give your answer some units. Don't clutter up the whole formula with every unit that's involved in there, but you must have with your final answer. If there are units, you must include them. Yep. Danny knows I'm hot on that, don't you, Danny? Because when people give me an answer in class, I say, well, onions, potatoes, carrots. Oh no, volts, right? Because it is important. Yeah. Otherwise, it's just a number.
Yeah.
Yeah. Sometimes the answer is just a number because that'll be a ratio where the units are the same. You divide volts by volts, it's just a ratio. Yeah. All right. So that's complex arithmetic. Just one more example. If we had the reciprocal, which we can get with impedances, sometimes we end up wanting to do a reciprocal of 2 angle 30 degrees. Effectively, all you have to do there is remember that this is 1 at angle nothing, and then treat it like a division. So that's a half at angle minus 30 degrees, that is. Yeah. Right. So, moving on then. Rectangular addition. Two plus 6j plus 4 minus 7j. How do you reckon we do that?
Add like terms.
Add like terms, yeah?
Yeah.
So you add the real parts.
Yes,
So it's equal 2 plus 4 plus 6j plus minus 7j. Like that, to put it in its full term, which, as you rightly say, is 6 minus j, and then whatever the units are would go on the end there if there were any. Yep. Okay, so that's fairly easy, isn't it? subtraction, 4 plus 6j minus 2 minus 8j. Similar. 4 minus 2 for the real parts. Subtract the real parts. Minus 6j minus 8j. Yeah.
2 plus 2 minus
You've got to resolve this bit on its own.
2 minus 14j.
Minus 6 minus 8.
Yes, so on this in brackets down 6 plus 8 14 minus 16.
Yeah. Correct. Yeah, that's right. Because that effectively becomes 6 minus. Yeah, that's right. Yeah. Okay, so that's subtraction. Right. Now, rectangular multiplication. Now, there's an argument that you could convert to polar and multiply. And I would say, yeah, that's okay. But what I wouldn't want to see done in a calculation is keep switching from rectangular to polar and back again, because every time you do that conversion on your calculator, you're probably going to do some kind of rounding of the numbers. Yeah. So I think it's important to know how to do rectangular and multiplication and division to try and save some conversions sometimes. It depends what form you want to end up in. If you want to end up in polar anyway, and it's not going to mean coming back again, you can choose the appropriate moment to do your conversion. I'm going to cover it anyway. 2 plus 3j times 3 minus 2j. How do you think we do that?
Yes, would be 2 times 3 is 6.
2 times 3 is 6.
And then that would be 3j times minus 2j, which is minus 6j squared.
Yeah, I'm going to put that over. I'm going to put that over there. Yeah. What goes in between?
Okay, yeah, you've got 2 times minus 2j.
So that's minus 4j.
Yeah, 3j times 3, which is not plus 3j.
Yep.
So you get minus 6j squared.
Yeah. What's j squared equal to? So let's just take this bit here a minute. That is equal to minus 6 times minus 1.
Yes, it's 6.
Yep. So effectively, let's just write that out again then. Qualifying that, we've got 6 minus 4j plus 9j plus 6. Yep. So it's got rid of the j squared term is gone. We can now pull together the two real parts. 12 minus 4 plus 9 plus 5j. So the j squared effectively changes the sign of that last term. Yeah? All right with that? Division. Now, this is where it gets tricky. Okay? The first thing we have to do is multiply top and bottom by what's called the complex conjugate of the denominator. In this case, e.g. 4 plus 3j. It's the denominator with the sign changed. Yep. So this is the process. We have to do 3, the numerator becomes 3 plus 2j times 4 plus 3j. The denominator becomes 4 minus 3j times 4 plus 3j. Yeah. Now, what I'm going to do is deal with the denominator and numerator separately over here. Denominator. 3 plus 2j times 4 plus 3j. That's 3 times 4 is 12. 3 times 3j plus 9j plus 8j, and on the end is 2 times plus 6j squared. Yep. Pull them together. This becomes minus 6. So 12 minus 6 is 6. 9 plus 8, 17j. So that's what would go on the denominator the next stage. 6 plus, hang on, 3 times 4 ain't 12, it's bloody 16. No, yes it is, 3, it's late in the day. 3 4s are 12, yeah. And 2, yeah, that's right, isn't it? 6 plus 17j will be our new numerator, multiplied out numerator. Denominator, we've got 4 minus 3j times 4 plus 3j, and this is where the trick comes in. 4 4s are 16. 4, we get a plus 12j. 4 times plus 3. 4 times minus 3 is minus 12j. Yeah. And then minus 3j times 3j is minus 9j squared. Yep. So these two cancel each other out. New j term. Okay. This becomes, we got minus 9 times minus 1. So it becomes 16 plus 9 equals 25. And it is always these two numbers squared and added together. Yep. So once you get used to this, you can just write that in. Because it is always that number squared plus that number squared. And that's it. And what you've done is you've got rid of the complex j term from the denominator. So that's 25. You then do equals 6 divided by 25, whatever that is. Yeah, you could do 6/25 plus 17/25 j, whatever it is. Eventually you might calculate that, depends what you're doing. Okay, I like people who like leaving things as fractions when they don't have to, but I find a lot of students don't like doing that. They like evaluating. But in that case, you're going to stay more accurate if you leave it like that. The only thing is, once you do any kind of conversion with your calculator, that ain't going to give you fractions, it's going to give you decimals for the two components. Alright? So it's tricky. It's more tricky than the polar method of division multiplication. But it can be done as long as you're careful. And the most thing you've got to be careful with is the signs of your numbers to make sure you don't get muddled up with them. Alright? Now, conversion. Calculated conversion. Uh, 4 plus 5j into polar. What we have to do on these Casio calculators, I'm just going to write on the board for the benefit of anyone watching the video, that you do shift followed by POL, and that's actually on the plus button on my calculator. And then you put in 4, shift, there's a comma, which is a shift function on the open bracket key on my calculator, and then you put in 5, you close the brackets, although actually you don't have to do that, and press equals, and you get your answer. So doing that, shift, polar, 4, shift, comma, 5, close the brackets. Equals. What you get is R equals 6.40 to 3. I generally work the 3 significant figures with these, and the angle equal to 51.3 degrees. So we're talking about 6.40 angle 51.3 degrees. Yep. So if you wanted to do some multiplication and you weren't going to need to come back again, you could convert from 4 plus 5j into polar and then do your multiplication division via that method. All right. And then the other way, sorry, I'll do polar. To rectangular. Let's convert this one back. 66.4 angle 51.3 degrees, and the way we do that is shift rec, which is on my minus button, followed by 6.4, followed by shift, followed by comma, followed by 51.3, close the brackets, equals shift rec 6.4 shift comma 51.3 equals, we get x equals 4.001. You can see where the error is in the fact that we rounded the numbers when we converted the other way, and y equals 4.994. Yeah, so that comes to 4.001 plus 4.994 J. Yeah, so that's fairly easy, but you could see that if you then went backwards and forwards several times, you could be compounding errors quite significantly if you're not careful. Yep. So convert by all means, as long as it's clear what you're doing, but don't go backwards and forwards too many times. Yep. So, using that arithmetic, we've got a circuit here with a power supply E, 1200 volts, and 3 impedances, Z1, which is a 60 plus 0J, so that's just a resistor. You should know that. It's only got a real part and no imaginary part. Must be a resistor on its own. Z2 is a resistor and an inductor in series. So 6 plus 12J ohm impedance. And the third impedance is a resistor and a capacitor in series. So it's got a 30 minus 30J ohm impedance. And the question is asking for us to find the apparent power, reactive power, and active power absorbed by each load, and the total complex or apparent power S. Okay? Yeah. So what I've done is I've got a slide with that made a little bit smaller so we got the information and we can go through it step by step. I'll just initially make a couple of clones of that page, I think. because we may need to. Oh, hang on, I'll transfer from it anyway. So, where do you think we could start with this problem? We're looking to find, ultimately in the end, ST. We also want to find, we know it's equal to, we also want to find S1, S2, and S3, the apparent powers of each of those three impedances. And if we find the S can be in this form, P plus QJ, couldn't it? It's complex form, where that's the power, P plus Q, and S is along there, and it's in complex form. We then, that figure would be how many watts it is. P watts plus Q vars, yep, times J. Right? Yeah, right, Danny? So how could we find S1? Using basic maths. If it weren't complex, if you weren't considering anything to do with complex numbers, how would you find S1? E times I, so that would be, in this case, E times I1, wouldn't it? Yeah. I1's an unknown at the moment, so first of all, we've got to find I1. How would we find I1?
E squared divided by r.
I?
Oh no, that's for S1.
Yeah. We could use the square, but with what we've got, that's the best way to find the apparent power. Yeah. So, but how do we find the current I? Using Ohm's law. E over Z1. Yeah. Okay. And what's E in complex form here? We've got to do it in complex form. 1200, angle 0 degrees. We're going to divide that by 60, angle 0 degrees. Right, Luke?
Yeah.
Yeah. 1200 over 60 is? Yeah. 20 amps, and the angle is nothing. Yeah. Therefore, S1 is equal to E times I1, which is equal to 1200 angle 0 degrees times 20 angle 0 degrees, which is 20 times 1200 is 24,000, and 0 times 0 is angle 0 degrees. Yeah. Quick question for you. What's that in rectangular form? How could I write that in rectangular form?
You just wrote it as 20,000 0.
Yep. That's VA. There's a VA in there, by the way. Yep. Which means P is equal to 24,000 watts. Q is equal to nothing. Yeah. So for a per resistor, S and P are equal to each other. Okay with that so far? Yeah. On my next page, I'm just going to split it a little bit and do I2, therefore, must be equal to E over Z2. That is 1200 angle 0 over 6 plus 12J. Right, what do we do here? Maybe the way I've done it in my example is to leave that as 1200 on its own and put 6 plus 12J underneath. There's a good reason why I left them in rectangular form. I want to know not only what S is, but I also want to know what P and Q are. So if I have it in rectangular form, I'll have P and Q already separated for me. Yeah. So we got to go down this route of doing this complex arithmetic here. That's going to be 1200 times 6 minus 12J on the top line, and because we've got to multiply by complex conjugate. Okay, speeding it up. What did we say about happens in the denominator? These two numbers squared and added together. Yeah. 36 and 144. I made that 180. Was I right? Yeah. Multiplying that top line out came out to 7,200 minus 14400J over 180. Please check, because I have been known to make mistakes. Enter Dan. He's looking for a good grade, which ultimately becomes 40 minus 80 J amps. I've done a conversion on that, and that come out at 89.4 amps angle minus 63.4 degrees. That's an inductor. That's the current. Does that fit in with civil? That answer. We've got 89.4 amps, and that's lagging by 63.4 degrees. Here's our word, civil. It's always worthwhile to check, does that fit? We've got an inductor in there. We've got no capacitance. We've got an inductor. Is the current right according to that? In an inductive circuit, current is after the voltage, should be lagging. It's a good sign we got a calculation right there. We ain't got in a muddle with the signs of any numbers. Yeah. Over this side, we then got to move on and say S2 is equal E times I2. So that's going to be 1200 times 40 minus 80J. Yeah, right. We got that right, which multiplies out to 48,000 minus 96,000 J, the units of S and VA. This bit is P2 equals 48,000 watts. Q2 equals 96,000 VA. Yep. Okay with that? Yeah? I'll agree with my figures. Just put a new one on there. Split again. I3 is equal to E over Z3. So that must be 1200 over 30 minus 30J. Right, and that's equal to 1200 times 30 minus 30J over plus 30J, correct, over 1800. Top line multiplies out to 36,000 plus 36,000 J. Divide all of that by 1800. And the final answer comes out at 20 plus 20 J amps. Polar wise, that converted to 28.3 amps, angle 45 degrees. Does that fit in with civil? We've got a capacitive part of the circuit, capacitive load, current is leading the voltage. Yep. So again, always a worthwhile check. Does it fit with that? So over this side of the page, S3 is equal to E times I3. That's 1200 times 20 plus 20J. That's 24,000 plus 24,000 J VA. And this bit is P3 equals 24,000 watts and Q3 equals 24,000 var. Yep. So the question asked for the total complex power ST is equal to S1 plus S2 plus S3. What we can do is write all them rectangular numbers. That's S1. S2. And add up the columns. We get 96,000 minus 72,000 J VA.
Will we have to put that at further right, isn't it?
No. What you really want is that converted. You can do it on your calculator,
yeah.
Or equally, we could say that is a triangle like that, where that's S, that's 96,000, that's 72,000, and we could do ST is equal to the square root of 96,000 squared plus, because you're only interested in the magnitudes here, if you square that negative number you'll get a positive number anyway, 72,000 squared, and that came out at 120,000 VA, or more appropriately 120 kVA. Yep. And as a check, we could make sure that all our P's powers add up to 96,000. Just do this, Danny. P1 was 24,000. What up? Yeah. P2 was 48,000, and P3 was 24,000. Yeah, they do, because they're the numbers in the rectangular addition anyway. Right? So it all works. Yeah? So, I've got a problem sheet that I'm going to give you at the end of this week for you to have a look at, and maybe we'll, because this is quite a full week, we might touch on a problem or two of them before we move on next week. We'll see how much we get done in the remaining time of day. All right, it's a pretty full week this week is. Are you reasonably happy with that? Yeah.
Yeah.
Yeah. All right, and that helps to, using the rectangular numbers helps to separate them terms S, Q, and P quite nicely, I think. Yeah. Power factor correction. Last week we discussed how low power factor results in a power line having to pass more current for a given load. We discussed how that leads to the supply authorities penalising consumers for poor power factor. Consumers can improve poor power factor presented by a high level of inductive load, because that's where it usually comes from. motors, transformers, lots of coils, high inductive load. Compensating for that by introducing what's called power factor correction. That PFC involves introducing a level of capacitance in the circuit which is said to provide reactive power to the source. What effectively it does is that we all know what it does, that stores some energy and then gives it back. So it works in tandem with the inductors to level things out a little bit. Okay? This goes some way towards counteracting the reactive power drawn by the inductive load. So it reduces that phase angle and the difference phase angle between voltage and current and gets T closer to S, or S closer to P, I should say. Because effectively P is the thing that stays the same, but by reducing the angle you make S, or the VA, smaller. Therefore the current is going to be smaller for the same voltage. So, reactive loads and power factor. The left triangle shows a reactive load with what's a low power factor, a big angle. So the bigger the angle, the lower the cosine of the angle is going to be. So what we got here is quite a steep angle, and the S line is quite long. Okay. When we add some capacitance, we'd end up with a Q value downwards as well as a Q value upwards, and we end up with what I'm going to call Q nu, which is effectively QL minus QC, a new overall reactive power. What that has the effect of doing is drawing this S line down that way, because the P line cannot change. The load is still the same wattage, so it's drawn this line down to here, reducing the angle, and therefore it's reduced the length of this line here, so your VA is less, and therefore your current, because the voltage doesn't change, if S is going to get smaller, that must mean the current is reduced. So we reduce the current in the line. Okay with that? Yeah? Luke?
Yeah.
Good?
Yeah.
Danny? And what you'll see, I know the company I used to work for, they'll have what's called automated power factor correction installed. So there's a controlled set of capacitors that will switch in and out as the load changes. So it will sense a change in power factor, and it will switch capacitors in and out to try and maintain it at a given level. What they don't do is they don't try and get it completely in line. They don't go for a cos theta of 1. Not fully sure exactly why, but there's a danger in going right on that line where your capacitive and inductive reactance are equal to each other. It's not a good idea in high power systems. All right. So, an example involving power factor correction. Okay. Now, for this question, for total real, reactive and apparent power, find that the power factor prior to correction, the total current flowing from the source and its phase angle in degrees, the value of capacitance required to reduce the power factor to at least 0.8 lagging, yeah, and the new total current when the correction is in place. So this gives you an idea of what difference adding some capacitance in afterwards does. Yeah. So I'm gonna go through. I've got a work solution for this problem. So we'll go through it quite quickly together, so that you can actually see what's going on here. Because a lot of this There's a little bit of a repeat of the problem we've just done anyway initially, but then the additional bit at the end. Okay, so first of all, we're going to find the current I1. We've done all this before. It's E over Z1 yeah, so that's that, and that's 200 over 100. There's no J terms in this, so quite quickly that's 2 amps, angle 0. Yeah, all happy with that. Yeah, or 2 plus 0J. I2 is E over Z2. That's 200 over 10 plus 20J. That comes out at 200 times 10 minus 20J over 500. I made that. Please check my figures just in case. I think they're all right. Which then multiplies out to 2000 minus 4000 J over 500, and eventually comes out at 4 minus 8 J amps. Right. That suggests that's lagging, civil, that's inductive, and we've got a lagging current. Yep. From that, S1 is I1 times E. That's 200 plus 0J times 2 plus 0J. Going to write it out in full just to make sure. And we got 400 plus 0J VA. Yep, for that, P is 400 watts, Q is 0 var. It's the resistive load, so we know that is true. S2, I2 times E, that's 200 times 4 minus 8J, that's 800 minus 1600 J VA, which is P is 800 watts, Q equals minus 1600 var. The question said total power, didn't it? Total power PT is 400 plus 800 is 1200 watts. QT, there's only one Q, that's minus 1600 var. So what we've got is we've got a triangle like so. There's 1600 there, 1200 there, and we can go ST (2000 VA). I'll do B on here because that's only a small one. I've got room for it. Power factor is equal to cos of the angle, put the angle in there, that's equal to 1200 over 2000, and I made that 0.6. Okay, so in its initial state, the power factor is 0.6. What did the next part of that question say, Danny? Yeah, so this is part C. We know that S total is equal to E times I total. Therefore, I total is equal to S total over E. That is 1200 minus 1600J divided by 200. Volt's got no angle associated with it, so that comes out at 6 minus 8J amps, and that converts to 10 amps angle minus 53.1 degrees. We know it's inductive in nature. Does it fit in with civil? Yes, a lagging current does fit in with civil. All right. So, thinking about this problem now of finding how much capacitance is as part D, we've got at the moment this situation, and that's 1600. We've got this as 2000 and this is 1200. Yeah, have I got all of that right? And that's watts var VA. This angle in here, because of that, is 0.6. What we want to do is get that in here, so the cos of that nu is equal to 0.8. Yeah. So what we need to do is introduce the QC down there that is the same length as that, effectively, don't we? Yeah. So if we can find out what this value is in here, Q nu in there, we can then take that away from Q old, and we'll know the length of that line, won't we? Because the length of that line there is that bit in there. So if we know this bit, if we can find that bit, we can take it away from that and we'll have what's left in there. You all with that? Yeah? So, how can I go about finding the length of that little bit of line in there? Q new. How would you go about it? We'll draw this little triangle out here. That's Q new. This is 1200. That's unknown. Cos of that angle, 0.8. What could we do? If you do, are you saying do the inverse cos of 0.8? Yeah. So what you can do, if we call theta nu is equal to cos to the minus 1 of 0.8. So we're going to find the angle, the new angle in there, Luke, yeah?
Yeah.
Right? That come out at 36.8 degrees. I rounded it down. So though the normal thing would be to round up, I've done it down because the question said improve to at least 0.8. So if we went the other way, we wouldn't get at least 0.8. Right? So what we've got now is a triangle where this is 1200, this is still Q new, and this is 36.8 degrees. Can we find Q new now? See the use of triangles, Luke? I was talking to you about that earlier. Draw one. Always worthwhile. What can we do now? Can we find Q new now? Which trig relationship would give us that? We got the opposite and we got the adjacent. SOC SOCTOA tangent. Yeah. So tan is equal to Q nu over P. Therefore, Q nu is equal to P times tan for the angle. That's 1200 times tan 36.8 degrees. I made that 897 var. So we've got to reduce the reactive power from the old 1600 down to 897 var. Yep.
Yeah.
Okay. So what we can do now is say, therefore, reactive power from capacitor is equal to Q old minus Q new, which is 1600 minus 897 equals 703 bar. Also, QC, we could also calculate that from E squared over XC. It's one way to calculate that reactive power. Yep. Therefore, XC is equal to E squared over QC, and that equals 200 squared over 703. I made that 56.9 units of capacitive reactance are capacitive reactance ohms. Yeah, well done. And we know that XC is equal to 1 over 2 pi FC, which rearranges to C is equal to 1 over 2 pi FXC equals 1 over 2 pi times 50 times 56.9, and I made that 55.9 microfarads. It's just about working with what you've been given and trying to work through it to find, and remembering that there are different formulas for calculating things. So as you progress through, the hardest thing with these problems is working out the method. It's a lot harder than the actual maths. You've got to understand all the different ways of calculating things and how they interact with each other. But none of that is anything more than Ohm's law, Kirchhoff's laws, and a bit of parallel and series impedance stuff. Nothing today we've done is anything more than that. It's just the numbers are a little bit more difficult to deal with. So the last bit of the question said, calculate the new current flowing, did it not? The new total apparent power and the new current. One more page. We've got, so our revised system has got an S up there. It's got 897 in there. P is still 1200. That doesn't change. Therefore, S new is equal to the root of 1200 squared plus 897 squared, 1498 VA instead of 2000. Yeah. A new IT is equal to S new over E 1498 over 200 equals 7.49 amps. So we reduced our current from, I think it was 10 amps, weren't it, to 7.49 by the introduction of that capacitor. Yep. Note, just going to go back here a minute to the page with this diagram on. Note that although there's some capacitance in the circuit, the angle is still the same side. You still have a lagging current. Still the circuit is overall inductive, because the bars up this way are bigger than them. So that's still line there. If you made this line longer than that one, then you'd draw S down underneath here, and you'd have an overall capacitive circuit. And you don't want that either, because again you're going to start drawing more current again. You're going to end up with a phase angle. So there's a balance to be made, and they do it, so they usually try and get it around 0.8, I think, somewhere between 0.8 and 0.9. Okay? If you haven't got any more questions about what we've covered today, I'm going to give you the tutorial question sheet for this week and let you at least have a look at it, and